probability techniques used to solve word problems at the end of the day. And one of the hardest things about teaching probability is that probability relies on sets and logic and counting techniques, which you need to fully master those in order to do it well. But we're going to go and skim through them very quickly. So what is the probability at the end of the day? What is the probability? Probability. Answer, it's a fraction. Just some number over another number, like 1 over 10, for instance. The example I'm going to use later on will be 1 over 100. Now, you wanted the complement of it, you just do 1 minus that, which is 99 over 100 as well. We'll refer to that later as well. So it's a fraction. More rigorously, if you define U to be the universal set, which is the set of all things you are allowed to talk about. And the universal set can be abstract as you want. It can be like the number of characters I'm writing currently on the screen. It could be the colors that I have on this text here. It could be the different types of text type fonts that I have here on this Microsoft Word document here. Doesn't matter. It can be whatever you want. Any subset of U in the context of probability is called an event. Let's call it denoted as A. Oh, and back to the universal set here. I don't want to go into Venn diagram talk. Oh yes, this universal set is sometimes called the sample space as well. So another name for U is the sample space. I really prefer to call it a population space, but well, we live in a society with systems and conventions. Anyhow, so A is a subset of U written like this. Then we define the probability of an event A to be number of possible outcomes. Sorry, number of desirable outcomes in your sample space over the number of total outcomes in universal set, in U or the sample space. And sometimes you might see it written in two different kinds of notation. You might see it written with absolute value vertical bars here. We call this the cardinality of A over the cardinality of U. Sometimes you might just have it as n of A, the number of items in A, over the number of items in U. And boom, straightforward like that. Now, there's one assumption we need to make about probabilities, and that's we agree that probabilities are bounded. Yeah, so assumption. Probabilities are bounded within the unit interval between 0 and 1, which is basically the same thing as going from 0% to 100%. And these probabilities are basically part of the real numbers. And we want to stick to this unit interval because there are already an infinite number of real numbers between 0 and 1. And it's been a while since I did foundations of real analysis, so I'm going to completely hand wave or ignore that part completely. Okay. Now I'm going to go and... Yeah, so that's an assumption that we take for granted. Given this, we can derive a couple of nice rules. So pretend in like the event set A and the universal set, or our sample space, that we have n items in total. Let me draw a picture here. First I need to go and make some room. Let's say I have event A here, and I define event A to be the number of dots, and U to be the number of dots as well. This is A, this is U. In U, there's only one dot. In U, I'm not going to be able to draw them all because it'll take forever, but let's say, for example, that we have 100 dots in here. Being lazy here. So if we were careful, we would go and define what these are. U and A are sets of the number of dots, drawn inside this ellipse oval. Now I claim that n of a, just based on the picture, is 1, and then n of u is 100, based on what I mentioned, which sort of makes sense, right? Here's an interesting thing we can do. Let's go and imagine this to be a bunch of dots, and we're picking one dot out of these 100 dots here. So you can actually think of it in this trivially equation arithmetic way, like the following. We know that's true that a number equals itself, right? So 100 equals 100. But if I were to go and take apart one unit from 100 units, I could sneakily just add a 0 pair to this 100 here on one side. So 100 equals 100 minus 1 plus 1. I'm allowed to do that. Addition and subtraction are opposites of each other, and I'm doing it on one side of the equation. This thing still holds true. But then, now for the magic of algebra, I can group these things together. This 100 minus 1 is the stuff remaining in the bag, oval, whatever, once I pick the dots out. There were 99 dots in total, and I only picked out one dot. So I basically partitioned or split this big set into two big sets. A and the stuff that's in U but not part of A, essentially. Well, let's go and generalize this. Let's say, look at the universal set here. Well, I'm garbling. Let's say in here, instead of 100 items, so we initially said this had 100 items, and this had 1 item. Let's pretend instead that this had n items. And this has r items. Again, we split it into 2. So we split or partition the set in 2. Well, then it stands to hold that n equals n, right? But I can add another arbitrary 0 pair of minus r plus r to this as well. So n equals n minus r plus r here. And then I group it like this. Based on how I define the event here, I can just simply define the probability of my abstract event to be, well, basically the number of dots I'm picking, which is r of them, over the total number of dots, n of them. If I were to take the probability of the complement, p of not a, I would be basically picking at the remaining stuff that's left after I picked out r items. So that's n minus r in here. So I just get n minus r divided by n in general. And let's see what happens when we go and add these probabilities together. P of not a. Well, that's just r over n plus n minus r over n. We can combine these into a like denominator. I get 1 over n, r minus r plus n minus r. The r's cancel out because they form a 0 pair, but now I get n over n, which cancels itself out, and I just get 1. So boom, there's one of our key rules in probability, the complement rule. P of a plus p of not a equals 1. And I can solve for p of not a algebraically by just subtracting p of a on both sides. So p of not a equals 1 minus p of a. And that's it. Aside from the complement rule, we can also do some 2 crazy additional things. One of them is a special addition rule for probability. But in order to really understand this, we need to go and introduce some extra notation. We need to use these symbols here. Let me write them up. This is called a union, and this is called an intersection. Union is analogous to OR in logic, and intersection is analogous to AND. Yeah, so union corresponds to OR. This corresponds to AND. which you'll then see that in terms of Boolean algebra or whatever, this is the same thing as addition, and this is the same thing as multiplication. Just take it for granted right now. Now, one thing we're not going to take for granted is the rule that we get from this. If we do the probability of A union B, so two events, let A and B, two events, two particular sets, we can draw them as circles or ovals. Then P of union A, or P of A or B. Oh, and note this or needs to be inclusive. Then this equals the probabilities being added together, the two events, minus the probability of the intersection of the two events. Something went wrong. P of A plus P of B minus P of A intersection B. Now you might be wondering, where does this intersection term come from? Well, consider the following. When you have like these two events, they might not necessarily be separate from each other. There's a big problem. Remember how I mentioned that like probability relies on counting? One of the biggest problems in counting, or the branch of combinatorics, is overcounting. You count more than what is needed. And this can happen in the following way. Let's say you have two regions drawn like this. So it's almost like a Venn diagram, but it doesn't have to be. It can just be any two arbitrary overlapping regions. And let's define a very abstract function or sequence define the function or sequence A of n A to be shading the area of region A, and then B is shading the area of region B. So going back to here, let's call this A, call the set A, event A, and this is event B. I'm going to shade them in two different colors. For A, I will do it in pink, and for B, I will do it in light blue. So we define it this way. Let's go and see what happens. I'm going to shade this very roughly, just drawing a bunch of lines to save time. And then we do the light blue. Do you see the problem now? We basically overcounted in the region in between events A and B, which is this particular little oval over here. Let me try and make it a bit thicker. So yeah. And that's bad, because then we're overcounting more than B, and that means then that our probabilities will be bigger than 1, which contradicts this complement rule that we derived, and the assumption that probabilities have to be between 0 and 1 in the unit interval. Where is it? Trying to find where I put it. Yeah, here. This assumption over here contradicts that. So that's no good. So in order to correct this, we have to go and subtract this intersecting term over here. And that's where this particular formula comes from, the addition rule for probability. So let me rewrite it again. Addition rule for probability. P of A or B equals P of A plus P of B minus P of A and B. Okay, however, there is an extreme case. And in fancy terms, A and B are mutually inclusive events in this setup. There is an extreme case, however. where A and B are mutually exclusive events. How does this happen? Well, it happens when the probability of A and B equals 0. And this happens by the intersection set basically being empty. It only contains the empty set. There is nothing inside it. So when that happens, very nicely, P of A or B becomes P of A plus P of B minus 0. And so the probability of A or B for exclusive events is just adding up the probabilities together. So that's where I said that OR in logic is analogous to addition in arithmetic, as shown above here. Okay, so this is the special extreme case of mutually exclusive events. We're almost done. Now, we're going to look at conditional probability. This one's going to be the hardest to go and try and understand and unpack because there's a couple of notation conventions that I really do not like, but well, I do not design the language this way. The mathematicians did, probably theorists or statisticians did, so we just have to go and deal with what we're dealt with. Again, consider two events, A and B, but let B, two events A and B, and they are all contained in U, the universal set. Then this formula applies. Okay, yeah, this is some really strange notation, especially with this vertical bar over here. And I already tried my best to go and use the and instead of the intersect notation just to make it more concrete and relatable. But this reads as the probability of event A given event B is the same as probability of A and B over probability of B. Now I need to go and define like these sets B and A very carefully. So sort of in the Venn diagram setup, which I sort of ignored to draw in the previous thing, you define the universal set typically as a rectangle, and this is U here. Now consider we have two events A or B, but I'm going to draw it in this particular way because P of B is in the denominator, right? And typically we want our sample space to add up completely to 1, right? Just based on the rules and assumptions I've shown you before. Well, then the set B has to be bigger than the set A. B would be like this, and then A would be a subset contained inside it, like here. So A is a subset, inclusive subset of B. What we are essentially doing in like an area drawing shading setup is that we are taking the area where set A and B share an intersection in common, this stuff over here, and then we're dividing it by like the original probability in B, which is this stuff here. And since both of these are probabilities, remember these are probabilities, not counting numbers, we're essentially going to be doing a fraction divided by a fraction. I'm losing my train of thought. Oh yes, this event A given event B, that's in the passive voice in whatever native language you speak. But I prefer the active voice. So this is the same as if event B happens, then event A happens. Which sort of makes sense. You go from the bigger set, and then you proceed to break down to the smaller set, this purple set over here. So that's where this thing comes from, and you have to divide by P of B. What this dividing by P of B does is it is reducing the probabilities such that when you go and add all the probabilities together, you make sure that they all sum up to 1. Because once again, we want that, in the simplest case, we want the probability of the sum of 2 events to add up to 1. And we want all the probabilities to be between 0 and 1 as well. That's the key assumption we want. So yeah, P of B helps make sure our conditional probability is contained in the unit interval. This process, and really handling this is beyond the scope of most high school courses, is called normalization. This will become relevant when you deal with probability distributions, but that's for another time. Okay, so at the end of the day, a conditional probability is simply a fraction over another fraction. So when doing P of A over B, then P of A, I'm going to write intersection notation now. This is going to be fraction 1 over fraction 2. So when you're doing conditional probabilities, if you're not dividing a fraction by a fraction, you're doing something wrong, unfortunately. Also, in algebra with conditional probabilities, it makes it's very useful to use this fact from middle school math that, like, say we have fraction 1 equals A over B, where A and B are integers or whatever, and then we have fraction 2 equals C over D. Then it follows that, like, A over B over C over D is the same thing as you keep the original fraction the same, and then you multiply by this fraction flipped upside down, or the reciprocal of it, D over C. So yeah, fraction 1 divided by fraction 2 equals the same as fraction 1 times 1 over fraction 2. Compound fraction rule for 2 fractions. Very useful, and you'll always use this. Now, just like the addition rule for probability, the conditional rule for probability, also known as Bayes' theorem, has an extreme case as well. Let's say that events A and B aren't contained within each other. They aren't nested within each other like Matryoshka dolls or something like that. Let's say they're completely separate and disjoint. So if I were to draw a drawing, the simplest drawing that represents this, it would be something like this. So this is a universal set U, and then I have the set A here, and the set B here, and they're separate from each other. 2 separate circles, like 2 chains which have been detached from each other if I stretch them out. And I can shade them in different colors if I want. Well, in that case, does shading A depend on shading B, and vice versa? No, it doesn't. I just shade A and I shade B separately from each other. In this case, that means that event A, and yeah, the event B is like the bigger event that you're dealing with. So in this case, I have, sorry, let me bold this too. Note, you have to be careful. It's whatever at the bottom here is to the right of the vertical bar. Yeah, okay. Let me repeat that again, but more slowly. In this notation conditional probability of P of event A given event B, whatever event is to the right of the vertical bar, that is what belongs in the denominator as a probability of whatever event you have. It's the one on the right, not the one on the left. So if I were to write this formula differently as P of B given A, you would get the intersection as well, but I'm dividing by P of A instead of P of B. I hope that makes sense, how it's different in this particular case. And the drawing will be different for here. But now back to the sorry, I'm going way too fast. Back to the extreme case for conditional probability here. Let's look back at the original formula. According to the picture, A and B do not depend on each other. So therefore, P of A given B is the same as P of A given A. And that, just by common sense or by convention, is just P of A by itself. So I basically end up with P of A equals P of A intersect B divided by P of B. Through some simple cross multiplication of P of B, I get that P of A times P of B equals P of A and B. This is the probability of two independent events. And is a special case of probability, which is basically how you see that and is analogous to multiplication probability. But this only works in a special case if the events are independent. They don't depend on each other. So to give a real life example, which happens like here, like pretty often, let's say that it's raining today or stuff. Does the probability of it raining today depend on whether it rained yesterday or 2 days ago, 3 days ago, or tomorrow? If it did, then it's dependent. If it did not, it's independent. So in the case where it's independent, you can just multiply the probabilities together. Oh, I forgot one last thing, which I really should have put at the beginning, but I guess I didn't think this way. So I define probability of A as n over A over n of U, correct? Well, what happens if A is essentially the same thing as U? Well, then essentially that's just taking the probability of the entire sample space, which is n of U over n of U, and that's always going to be 100%. Probability of selecting the entire sample space, there's only one way, and that can be done with 100% accuracy. So that's the last step here. Let's see. What am I trying to think of else aside from here? Oh yes, I guess like it's I'm thinking of a generalization. Again, with the addition rule of probability, you have to be careful that there's no overcounting here. But assuming that there is no overlap, and then again you have to be careful with the number of events you have, you can just add finitely all these probabilities together. So let's say, and yeah, this is the most flimsiest explanation over here, or most hand-wavy one right now by far. Let us say we have a finite collection of events. Call it A1, A2. I'm going to index them, A3, AN. Picking any event in this list is picking AI. It stands to say that the sum if I take the sum of these probabilities, yeah, let's not use the sigma notation. If I take the sum of these probabilities, AI, then I can just add them up together like this. I'm not going to put the free here, I'm a bit lazy. Dot 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 plus, that means, this dot 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 means there are truncated terms which are abbreviated and not added here because it'll take too long to write them down, up to the very last event, A of n. And that is assumes your events AI are disjoint, which means there's no overlap, and therefore no overcounting. And that's it. That's really basically like the main rules you have. Oh wait, sorry. Yeah, the sum of these probabilities, when you add them all up for a sample space, that should give you 1. That should give you 1. Yeah, there, that's the rule. And in general, as a result, that's it. So I think that's like 5 rules and assumptions dealing with probability. Let's go and put them down nicely in the end. So in summary, assume that all probabilities are between the unit interval 0 and 1 inclusively. We state that the probability of event happening and the probability of its complement happening will add up to the total sample space. Oh, this is where I should put it. The probability of taking the entire universal set will obviously be 1, the entire sample space, because 100% of the probability of an event happening and its complement add up to 1. The addition rule of probability states that P of A union B equals P of A. I need to put this on another line. P of A union B equals P of A plus P of B minus P of A intersect B. In the extreme case, yeah, so you have an extreme case. Oh yeah, I forgot what to say what this is called. This is called mutually inclusive events. Two mutually inclusive events. Extreme case, when the intersection is empty, and hence the probability of the AN be 0, then we get P of A union B equals P of A plus P of B, which are called mutually exclusive events. And finally, we have the conditional rule of probability. I'm getting ahead of myself. Okay. Yeah, I forgot the last caveat. Why is it not? Please give me a second. We are experiencing slight technical difficulties here. Okay, fine. I'm gonna have to go and cut and copy paste this here. Okay, there we go. I have a finite collection of disjoint events. So that basically means no overcounting. Then it follows that sum P of AI equals P of A1 plus P of AN. Summing up all the probabilities in a sample space gives us 1. And that's kind of related to point 2 here as well. Okay, now finally conditional rule of probability. That's that P of A given B equals P of A intersect B over P of B. And in the extreme case, when A and B are independent, P of AB becomes P of A given A, which is just P of A. So therefore, P of A intersect B equals P of A times P of B, which are called two independent events. Which is a multiplication rule of probability. And let me go and two mutually inclusive events. Is that it? Is that it? Yeah, where P of A is a real number. Or P of A is a real number. And yeah, that's it. That's essentially it. Okay. Let's see if I can get it in one page. Yep. So feel free to take a screenshot of that if need be. And that's basically how all you need to go and solve, in the most simplest sense, probability techniques for probability word problems or abstractions. Later on from this, I will go and talk about probability distributions, particularly the difference between discrete and continuous distributions, and some particular special types of them. But I will be focusing only on the special distributions that are focused in the IB diploma unit. Okay, I hope this satisfies everything. Until then, I'll be heading out now. Thank you. Hope you enjoyed the video. Please like and subscribe. It really helps out the channel.